Today we are going to teach the squeeze theorem, sometimes called the sandwich theorem. In plain words, if one sequence is always trapped between two other sequences, and those two outer sequences both converge to the same limit, then the trapped sequence is forced to converge to that same limit too. Let us set up three sequences, call them a sub n, b sub n, and c sub n. Suppose that for every n, a sub n is less than or equal to b sub n, and b sub n is less than or equal to c sub n. Suppose also that both a sub n and c sub n converge to the same limit, which we will call L. We will prove this fully using first principles, and then afterwards we will show a genuinely different proof using limit superior and limit inferior. First principles proof: pick any small positive tolerance, epsilon, greater than 0. Because a sub n converges to L, there is some point far enough along the sequence, call it n sub 1, after which a sub n stays within epsilon of L. Because c sub n converges to L, there is likewise some point n sub 2, after which c sub n stays within epsilon of L. Now choose n to be the larger of n sub 1 and n sub 2. This gives us one shared starting point far enough along where all three tolerance conditions hold at once. Past this point n, we know three things together. A sub n is greater than L minus epsilon, c sub n is less than L plus epsilon, and b sub n sits between a sub n and c sub n. Combining these, past n, b sub n is greater than L minus epsilon, and b sub n is less than L plus epsilon. That means b sub n is always within epsilon of L once we go far enough along. Since epsilon was any positive tolerance we like, and we always found such a point n, this is exactly the definition of b sub n converging to L. So the trapped sequence must converge to the same limit, L check step. Notice the whole argument rested on squeezing from both sides, using one shared far enough along point, so the proof is complete and consistent. Now let us switch to a genuinely different proof method, using limit superior and limit inferior rather than chasing epsilons directly. Recall that limit superior of b sub n is the largest value that b sub n keeps approaching infinitely often, from above, and limit inferior is the smallest such value, from below. Since a sub n is less than or equal to b sub n, taking limit inferior of both sides gives limit inferior of b sub n is greater than or equal to limit inferior of a sub n, which equals L, since a sub n converges to L, since b sub n is less than or equal to c sub n. Taking limit superior of both sides gives limit superior of b sub n is less than or equal to limit superior of c sub n, which also equals L. So limit inferior of b sub n is greater than or equal to L, and limit superior of b sub n is less than or equal to L. But limit inferior is always less than or equal to limit superior for any sequence. Squeezing these two facts together forces limit inferior of b sub n to equal limit superior of b sub n, and both must equal L. When limit inferior and limit superior of a sequence agree, the sequence converges to that shared value. So b sub n converges to L, matching our first proof. This route is genuinely different because it works entirely through order properties of the sequence without ever picking an epsilon or a starting point by hand. Now let us look at why both an upper bound and a lower bound are truly necessary using a pathological example. Let a sub n equal 0 for every n, so this constant sequence converges to 0. Let b sub n equal n itself, so b sub n is 0, 1, 2, 3, and so on. Notice that b sub n is always greater than or equal to a sub n, so we have a lower bound converging to 0. But there is no upper sequence here squeezing b sub n back down towards 0, and indeed b sub n equals n grows without bound, running away to infinity, even though its lower bound sits happily at 0. Check step. This shows that one-sided control alone, just a lower bound converging to a limit, is not enough to force convergence. You genuinely need both an upper and a lower sequence, squeezing to the same limit for the squeeze theorem to apply.